We're now going to talk about state feedback. So in state feedback, we have our state model, x dot is equal to ax plus bu, y is equal to cx plus du. We're going to use this control law. U, the control signal, is given by some constant times the state, and here we have another input. In a block diagram form, it looks like this. So here's our other input, r. U is then equal to the sum of these two guys, and we're actually somehow getting the states out of the system, and then we may have another output y here. And so this is what's called the control law, and the word law here is similar to the usage of the law of gravity, for example, or Newton's law. It prescribes a physical relationship. So that's all it means. All right. So, and that's a common term that's used in systems. So when we apply the control law to the system, this is what we get for our overall system. We get a new A matrix. In fact, we get the matrix A plus BK. And so the question is, can we choose, for example, K to stabilize the system or put the eigenvalues in desirable locations? And so we have this result already, or rather this definition of stabilizability. A system AB is stabilizable if and only if it has no unstable, uncontrollable modes. We saw also earlier the concept of a state feedback fixed mode, that there are no unstable state feedback fixed modes. So if the system is controllable, then it's automatically stabilizable because all the modes are controllable, stable and unstable. If the system is stable, then the system is stabilizable because there are no unstable modes. So there can't be unstable, uncontrollable modes. And finally, a stabilizable system might be neither controllable nor stable. So we can have that situation. So the stabilization problem. Under what condition can we find a K to stabilize the system? And here's the fact. There exists K that stabilizes the system if and only if AB is stabilizable. So basically what this is saying is, if it's stabilizable, there's a K that stabilizes it. Okay? I can use state feedback to stabilize it. So that's cool. And in fact, this is one of the powers of state feedback, is that state feedback works where other types of controls may not work. The pole placement or eigenvalue placement problem. Under what conditions can we find K to place the poles of the system where we want? And here's the fact. Again, we've seen this already. There exists K that arbitrarily places the eigenvalues of the system if and only if AB is controllable. So we have that situation. We've talked about state feedback fixed modes or uncontrollable modes, and so we saw that if lambda is an eigenvalue of both A and A plus BK for all K, then lambda is called a state feedback fixed mode, and we've already shown that such an eigenvalue is an uncontrollable mode, and so we have that. A fixed mode is equivalent to an uncontrollable mode, state feedback fixed mode. So in this case, suppose there is a lambda so that I can factor from the characteristic polynomial of A, s minus lambda, and also A plus BK, I can factor s minus lambda for some polynomials P1 and P2. Okay, so in this case, we have this situation. We can factor some constant term out of both of these polynomials. So here's our state feedback system after we've applied state feedback. And so we want to ask the question, how does state feedback and controllability relate? So the statement is, state feedback does not change controllability. That is, AB is controllable if and only if A plus BK and B is controllable. So this shows us that controllability is not lost in the system. So one way to see this, and so a quick proof here is, assume this is not controllable, then I have a left eigenvector such that WB is 0. So if I multiply W times A plus BK, I can see that that is equal to lambda times W. That is, it's an left eigenvector of A plus BK, and the same WB is equal to 0. So this basically shows that the two are equivalent to one another. So it actually does it by contrapositive argument. Finally, the poles of the system are affected by state feedback, but the zeros are unaffected by state feedback. So here's the system in the state, here's the system matrix in state feedback. And what we show is that I can factor this matrix this way, And so this shows that for the values of S, the rank of this is the same as the rank of this. Okay? The ranks of the two systems are equivalent, even though we're applying state feedback. And the reason is that this matrix product has the same rank as this matrix because this matrix is non-singular. We can show that this matrix is non-singular, so the rank of this product is just equal to the rank of this quantity. So this is saying that the rank of this matrix is equal to the rank of that matrix. And so we have, whenever this drops rank, this drops rank. Similarly, whenever this drops rank, this drops rank for those same values of S. So we have the invariant zeros are unaffected by state feedback. Stay tuned and we'll talk a little bit about Ackermann's formula.